Hi everyone. I hope you can hear me well. Um, so today's menu du jour is about LLM evaluation. So it would be pretty high level, except maybe for the end where I would present more like an AutoML application for LLM evaluation. I suppose you're more familiar with AutoML, so enter slightly into more detail. But most of the talk would be pretty high level. Yeah, and so the goal of these lectures are that you become familiar with the main families of methods that are used to evaluate LLMs, that you understand the kind of the key difficulties to evaluate LLMs, and that you also get ideas and low-hanging fruit about how AutoML can be applied for LLM or LLM evaluation in particular. Okay, just so that we are on the same page, I mean, to build an LLM like Gemini or, Llama 3, there is a whole life cycle. So it really starts by gathering a huge corpus. Then there is pre-training, you get a pre-trained model. Then you do some, sometimes called post-training, fine-tuning, RLHF, instruction tuning, and you get a model that you can talk to. And then you want to obviously to evaluate it. So I don't know, you want to choose between Gemini and Claude, and you get, I don't know, a trusted instruction tune model or a model that you think is better. And then obviously at the end there's also this model, you put it somewhere and you do inference. And so what we are going to focus most is kind of this stage is just one of the stages of the life cycle. Okay. I should put the time. I should say also, like, please, anytime, if you have any question, please interrupt me. There will be some questions for you also, but I'm happy to have any discussion during the talk. All right, so LLMs, they take as input free text, they output free text. So, how do you select an LLM given a list of like 500 plus kind of model? And it's quite difficult because how do you evaluate a model that can output any sort of text? So for instance, how here, can you see my mouse? Yeah. Can you recommend a 2-day trip to Hawaii? If you have two options, how do you say which one is the best? Or like compare and contrast renewable versus non-renewable energy sources. I mean, this is clearly a challenge. So the kind of current challenges, well, okay, no, yeah, that's just a high-level view of the kind of challenges. Like we'll dig into most of those, but so there's just this open nature, so that's open text, so that's hard, it's ambiguous. You have many languages, so now models speak 30 plus languages, many objectives you want, and also there is a cost that in some cases can be very expensive. So for the multilingual model, so I don't know if you try, but you can chat with ChatGPT and others in, I don't know, French, German, and that's, and so you need to evaluate models for every language. And so I will have a question for you. How would you do like a LLM evaluation for the multilingual, I don't know, in your mother tongue or like, let's say 30 languages?
Come on.
Yes.
I would start with like setting up data sets where you have like clearly defined questions.
Uh-huh.
And like they can be posed in English, but I heard that the answers have been in several languages.
Mm-hmm.
And then I would like start trying to capture this a very diverse set of like questions. I don't know.
Yeah.
Starting from logic, going over like just some regular knowledge and so on. And I would try to, for each of the topics, I would try to like capture the multilingual aspect.
Okay, that's a very good and thorough answer. And so I guess you say the answer would be in the target language, and I guess so the question, right? And you will generate those for like a variety of topics. And I guess one challenge that you have, so let's say if you have like 40 languages, it may be difficult to have a good coverage of a.
I mean, it probably goes down to just like, I would just guess that it might go down to just like setting up these extensive like data sets.
Uh-huh.
Trying to, the question is to somehow automate this process of developing this like data set probably, because it's just incredibly annoying. But I don't know.
Okay. Yeah, that's fair. I mean, it is annoying. It is also quite, I guess, important because I mean that's ultimately like those are kind of the scores that you use to in your model development, and but it is challenging to do a lot of languages for a lot of tasks, as you say. I mean, there is really this issue to cover all the languages. In particular, some languages. I mean, you can always crawl data somewhere, but like some. I don't know, there will be obviously less data for, I don't know, Portuguese than kind of, yeah, English or Spanish. This is, if you are interested in this topic, I recommend this paper that gives a good overview. I mean, they survey, they say 2,000 plus. I mean, they mostly prompt GPT to survey 2,000 plus, but still, and they do a lot of interesting analysis. Here in the plots on top, you see the number of benchmark per country, and it is as you would expect, I suppose. So US and China has like kind of, I mean, maybe, yeah, 1,000, I don't know, 200, 300, yeah. Many hundreds of benchmarks, but I don't know, in Africa, like in a lot of countries, you will have maybe one, maybe zero. And if you go to like a lower frequency languages, I don't know, like French or German, which are still kind of frequent, but this also go down by a lot. Yeah, so that's kind of one issue. So in your answer is very good. I mean, like I guess one natural thinking will be like maybe I'll take. I mean, of course, in English there are a lot of benchmarks. So they, as you say, they cover a good set of topics with question and answers that are kind of deterministic. So you could think about just translating everything. And this paper analyzed that a bit. It is clear that with translation, you get something that is kind of a bit suboptimal. So yeah, of course, you get everything very fast. But I mean, I guess you get two main issues. I mean, of course, translation is not perfect. It's a bit noisy. Maybe, for instance, if there are like some questions that are really about the subtlety of language, obviously the translation is going to mess up. So you can use human translation, but it's a bit more expensive. But a problem that you keep is that you would keep like a very, I would say, cultural and kind of bias of like some of those benchmarks. So we will see a bit later. But for instance, the benchmark developed for US, they have a very US centric point of view, right? I mean, they will ask a lot of questions about US history, and it may be different from the question that you will think of, like if you are, yeah, obviously in China, Europe, or Africa. Okay, so I mentioned also that you have many objectives. Those are objectives that are, I mean, really present, that you want to evaluate, so many dimensions. And all of them may give you one number if you aggregate the benchmarks. And so it means that you, for each objective, let's say for safety, you need some benchmark. You also need them for style or fairness. And it's a big question, how do you combine all those objectives? Okay. Yes. I mean,
like, is this something people do? Check whether, I don't know, the latest data has been learned properly.
Yeah, I mean, that sounds obvious. I don't have a reference. I mean, there must be some paper that do it, but I don't have a reference. But that sounds like a good yeah, a good idea. And yeah. Okay. So that was, I guess, a very high-level introduction, and now maybe we'll take a look about different type of methods for evaluation. So, yeah, and mainly it's going to be two categories. It's a simplification, but I would say one category is static evaluation. So it's really what you were saying. I don't know. I define a set of questions. I have a fixed set of answers. And there you prompt an LLM given a fixed set of a fixed question, for instance, to choose among 4 answers, and so yeah, you know the answers, so it's easy to evaluate in a sense. Those are typically the cheapest benchmark because you just need to do inference, and maybe if you have like 4 answers, you just need, I mean, just choose between A, B, and C, and D, and that's kind of the cheapest. One downside, though, is that obviously your LLM, they may have great score static benchmarks, so they know how to answer all sort of questions, but you can't talk to it, right? Or it's a very unpleasant, or it's very unfair, or it's very, I don't know, it's insult you, or like you just evaluate one aspect. Right, so it will be very low utility if it, I don't know, it always refuses because it thinks your question is how to say, like not safe, or like, or it's too toxic, and so on. So just doing a quick overview on static benchmark. I mean, there are a lot of them. MMLU is clearly the most known benchmark, so that's used all over. And it is a large, I think it's like 57,000 question and answers that are based on US exams. So it's very thorough and covers a lot of different topics. So that in this sense is pretty good. There are many others, obviously. And as I say, you prompt an LLM to answer questions. So there is this 0 shot, few shot thing. It's just like if you provide some example of a correct answer or not. So this is, for instance, one example from MMLU. But I think it's undergraduate math, like find the product of the given polynomial in the given polynomial ring. So f is this, g is that, and it's in Z8 x. And so I would be keen to know if like who wants to take a stab at the answer. Who thinks it's A, B, C, or D? Maybe you can read the question for, I don't know, 10 seconds and think. And okay, who thinks the answer is A? Who thinks the answer is B? C? No one? Oh, you think it's C? Okay. And D? Yeah, I mean, so I guess this Z8 is kind of confusing. So that the point is, well, okay. Can you answer this MMU example? Actually, I have to think. I think the way you can just get the constants. I think it's -5 times 2, so it's -10, and then modulo 8. I think the constant should be 2 or 6. So I guess it's B. Yeah, you say B. Yeah, right. That's I think B is the right answer. And just think about it. It's hard to poll, but what do you think is the accuracy of like a 8B llama 3 model on this? I mean, just try to think. And so the accuracy is 73%. So this includes a lot of questions like this. So that means that those models are quite, I don't know, I just want to say they are kind of quite good already. But yeah, this is just one aspect in the MMLU. We could maybe, if you look at Hugging Face and look at all the categories, I think there are like 50 categories or something. Yeah, you will see a lot of things about history, psychology, and so on. Okay. In case you ever want to evaluate an LLM at home, or like there are a lot of frameworks for that, so you don't have, I mean, you mostly don't have to do anything, so you just have to tell the model and so on. Harness, Late-Eval, and Helm are the main frameworks. If you want to use, for instance, Harness is probably the most used framework. It's really like that, so it's really super easy. Right. Now, this is good for static evaluations, but as we saw, often things are kind of dynamic. So like we are looking for models that we can chat with, that we can ask open questions, so that the static questions, they can only kind of measure world knowledge in a sense. Now, I have this question for you. How would you do dynamic evaluation? Right? Oh yeah, you have.
Kind of depends on the use case.
On the use case, yeah, okay.
One thing you do is use LLM plus, so you use
Uh-huh.
LLM to base the algorithm from LLM.
Mm-hmm.
And for that version of some problems, obviously it also fails as many different
Mm-hmm.
solutions. Or you could also just use different similarity scores, so bringing the text,
Mm-hmm.
personalization of the text. You could look into the similarity score and check how similar this property generates.
Yeah.
That should be with our original result. So that doesn't work.
Yeah, I mean the second is really what machine translation, I guess, was doing for some time. Like they use Bleu, no, I think it's Meteor, but it's like you have a golden answer and you look at some kind of similarity, and that's the two. And those are two kind of good approaches. And I guess there would be another one. Maybe it's obvious, but I mean you could ask humans, right? I mean like so human annotation. So for instance, let's say on all these questions, you have 1,000 questions, and you ask them do they prefer model A or B, and you do some sort of win rate. Right, and it's actually funny because I would imagine that it's the first thing that comes to mind, and the one that you say, the two that you say are more maybe advanced. But yeah, and LLM has well, okay, so human annotation is a way. So typically, you will have a set of a lot of questions, and then model completion from, like, say, Claude and GPT. And so you ask a human, it gives a preference, and then, well, you can do many things. So you could do win rate, you could do some ratings that compare the models. So that's the ideal metric, but it's very expensive. Also, like annoying thing is it's very slow and asynchronous. So like, let's say you are developing your model, you evaluated your new, I don't know, learning rate or data set. I mean, maybe you have to wait a day or two to get all this human annotation. So that's something that is kind of, annoying. And the other approach that you were mentioning is LLM as a judge. So you replace a human by an LLM judge that will just be prompted to judge like a human, and will also return a label. So yeah, okay, my annotation got messed up a bit, but so for chat capabilities, we clearly need dynamic evaluation. So LLM as a judge and human annotation is one way. I want to mention Chatbot Arena. I will talk about it also later. This one uses crowd annotation. So I mean it's actually worth to take a look. You can see my screen, right? Okay. Okay. So we could ask a question, for instance, what is the best hyperparameter optimization method? Like to ask a very neutral question, and so we will live. It generates two answers that are, I mean, okay, here grid search, random search, Bayesian optimization, population-based method, gradient-based, multi-fidelity, practical consideration, blah blah blah. And this one, there isn't a single best. It depends on your specific situation. And mention a couple of things. So as a user, basically, you will read those texts, and what is the final recommendation? Yeah, okay. So well, I should have asked like, which one do you prefer? I don't know, the left looks slightly better, but yeah. So I voted for the left. It got a victory, good for Quen, and from those, there are some leaderboards that are generated. I'm gonna go to the legacy because they changed. I think they changed it a week ago. I have all my slides, and I was slightly pissed off. Okay, yeah, and then you go to the leaderboard, and well, okay, so all models are ranked with those battles that are gathered by people voting. So maybe you've heard about Chatbot Arena. It's very famous. In case you have not, it is really a big go-to platform. So getting high on this leaderboard is a big deal. So for instance, I don't know, when there was this Grok model from Elon Musk, they really try to get a high position, and yeah, and it is quite visible. This is a ranking that was available, I think, 1 or 2 months ago. At the time, Grok was first. I want to just point out a few things. So the best open model was top 6. So that's DeepSeek. Sorry, the best open weight model. If you want an open weight model with code available for the post-training, you have to go to the 46 position. And if you want a model that is fully open, so open weight is not open source, so you don't have the code to train, you don't have the data. You have to go down to 153. So just want to mention that. So one thing about this approach is very expensive. So if you count the number of battles that you need to have to properly rank a model, and you use kind of like US salaries, like I think minimum salary, I think you end up with a cost about $3,500 per model to evaluate a single model. So I don't know, there are like hundreds of models, so that would be quite expensive. Right. Yes.
Just a question to this. I mean, if I can just go to a website and I'm like, I don't know, let's say, I would argue that this might not also depend on the use case. I mean, if I were to use a model for like proper work, I would like really go through the answers and really compare them and so on. But if I'm just looking something up, as you did, I would read like the headlines, and then probably like the model that structures the text in a better way always wins.
Yes.
So I see the point, like you want to objectify something, but I mean, if you were to measure like correlations inside here and see like, okay, does it correlate to the structure or actually to the content and so on, what would you say, like how objective?
No, I mean, it's a great point. I mean, actually, if you look at here, the second column is rank style control. And I mean, in this particular case, I don't know, but I know some papers, they have a cousin model for the style, and then they remove this effect. Because, I mean, actually, and you saw the model, well, I did not read like the answers kind of thoroughly, but I think most people don't. And I chose, I mean, the left answers, I think, were maybe listing the key methods a bit better, but also it has better formatting. And that's indeed like very, that impacts the scores a lot. That being said, I mean, it's important for model output to be well formatted, right? So that's but it's ongoing kind of discussion. Also, there was a big controversy recently with Llama 4. So Llama 4, they had like very, very good position on the leaderboard, but it was, I don't know, it was like a specific model that was fine-tuned for the Chatbot Arena, and that was outputting a lot of emoji. And the model that is on Hugging Face actually had like way worse rank. So that's, yeah. But and to the first point also, sorry, that you were making about different categories. This is also very important and very valid. In Chatbot Arena, you have also different kind of I don't know, categories. Like for instance, coding. So it's maybe not the same as like asking a trip to Hawaii. And this is one way to do. There are also some papers that would generate some benchmark on the fly. So to say, like for instance, you say I want a model that is good. I don't know, for coding. And we'll talk about that actually a bit later. Okay. So as I said, this is fine. I mean, they still have some issues, but it's actually very expensive. And so you will want maybe to do better, so at least to have a way to trade off cost for accuracy. And accuracy being, for instance, let's say you want to have ranks like from your benchmark, your method, that are close to the, let's say, Chatbot Arena, if this is your gold standard. So here I'm showing all those benchmarks. Essentially, you can analyze it like this. So like if you were to rank models using this benchmark, how close would that be with Chatbot Arena, which is human annotation? So our Chatbot Arena, of course, has a correlation of 1 with itself. Actually, okay, if you see slightly below in Chatbot Arena, English is like, I think 97%, or 96%. So yeah, if a paper has a correlation that's higher than 96, maybe it's a bit doubtful. And right, and then for instance, MMLU that I mentioned, I mean, it's here, and it's a correlation of like 80, I don't know, 2% or something, and the cost is $10 because I mean, you have actually 50,000 questions and you need to go through, and this has a cost, right? Like, so if you, for instance, if you have a 70B model, this is not a zero cost. LLM as a judge, LLM as a judge are, those Alpaca Eval Arena hard. We will talk in detail about LLM as a judge at the second part of the talk, but they have pretty good correlation while decreasing the cost. Yeah. And then MMLU. Mix Eval and Mix Eval hard, I mean, they look like they are very nice on the Pareto front. I'm not talking that much about it because, well, it's only a static benchmark, and I'm not sure if the correlation is, how to say, if the correlation they report is the correct way to do that. So, okay, so LLM as a judge, again, back so that let's go to slightly more detail about this one because it's an important family. So you ask an LLM to judge if an output is better. How do you do it? So you ask the model you want to evaluate to generate outputs. You also ask a baseline, for instance, GPT-4 to generate outputs. So it looks like this. For instance, let's say this is Llama 3, this is GPT-4o. And then you ask an LLM, okay, here are 2 instructions, tell me which one is better. And it will give you a score. And from that, you can compute, for instance, a win rate against your baseline. And then for each method, you have a number, and you can rank them. And well, for instance, you can do a leaderboard, or you could optimize the win rate with hyperparameter optimization, for instance. Though, I mean, nothing is perfect. So for LLM as a judge, you have a few issues that were mentioned earlier. I mean, that's true for human too, but LLM as a judge, it has been shown they prefer verbose outputs. So if you output something that is longer, typically LLM as a judge prefer it. Generally, they are quite attached with the style, maybe a bit more so than humans. If you do it naively, there is a bias of the position. So if I go back to my example, sorry, I went a bit too far. But here, I mean, you could ask the same question in permute model 1 and model 2 and get a different answer. And if you do that, they appear to slightly prefer the first answer. So that's a bit annoying, but you can just do the 2 order and take the average, and you get rid of this problem, but it's slightly annoying. Of course, there is some data contamination possibly. So let's say if you have a leaderboard with the same set of questions, I mean, people could just fine tune on it. So, I mean, you can, like for instance, how in AHA, they have a set of questions that that they are supposed to refresh. I don't think they ever refresh it, but they say they could. But I think those are maybe small issues. They are like bigger issues. So one big issue is that, I mean, I was very surprised, but most papers actually don't do cross-validation. So, I mean, for LLM as a judge, you have a lot of kind of model choices, like hyperparameters, and you are picking them based on a score, and so your score it should be a validation score, and you should have a test score. But all papers were doing the Spearman correlation with same set of models. So obviously, and then that's how they get like this Spearman correlation of like 95%. It's sometimes as good as just using English in Chatbot Arena, but it is yeah, really wrong. But I mean, I guess you can fix it as you want. So obviously, if let's say if your metric is how well you can rank models, you should use a different set of models to evaluate and select your models than to report your performance. I mean, that's clear. A big issue is that the judge, they tend to prefer their output. It's weird, I mean, why they do that, but like, so for instance, GPT-4, it tend to prefer output from GPT-4. But the thing is, I mean, all this LLM as a judge, they use GPT-4 as a judge, and there is a self-reinforcing thing. Also, GPT-4 it's not even open weight, so it is not great. So yeah, I mean, Sota judge, they use closed models, and this clearly poses some issues. And okay, so the cost of the evaluation, so it's not thousands of dollars, but it's yeah, $20, $25 to evaluate one model. It is still annoying. So for instance, if you want to do hyperparameter optimization and you want to evaluate 100 choices, this cost is going to come for you. Okay. So for this, we talk about model family. I just want to talk about kind of leaderboards in general. It's, I guess, a similar topics. We'll also talk again about Chatbot Arena. But I mean, leaderboards are clearly quite important because they help to standardize the evaluation process. So everyone evaluates the same thing in the same way. And I mean, that can, in some cases, that can really help to steer the community into kind of a single direction and put all this mass. So for instance, ImageNet, that's a great example, I think, where, I mean, for years, people try to improve on it, and that really led to like super efficient architecture that then worked like so well across many use cases. And so for LLMs, obviously, you have a bunch of leaderboards. So some are static. So like, for instance, they consider data sets such as, I mean, benchmarks such as MMLU and so on. So there is OpenLLM leaderboard, Helm, and some are more kind of, you'd say, kind of dynamic. So Chatbot Arena and OpenWater, like Bench LLM, which generate like fresh questions. Some are dynamic but synthetic. So they use, for instance, LLM as a judge. So that's Alpaca Eval, Arena Han. And they have also translated version, which allows to do this multilingual thing for chip, but maybe not in a perfect way, but at least you can have a score in Spanish, right? You just translate all the prompt and use an LLM as a judge that judge like Spanish answers, for instance. Right, so we'll just look into two leaderboards, so OpenLLM leaderboard and Chatbot Arena. Okay, so OpenLLM leaderboard. So it was created in 2022 by Hugging Face, and it basically took the average scores on a list of static benchmarks. So the list of benchmarks got updated 2 times. So the models were evaluated for free on Hugging Face clusters. So whenever they had like the cluster idling and some node idling, they were like pulling jobs from the community, submitting to their queue, and evaluating them. So because of those reasons, like fully open, free compute, it was widely popular. But it ended in April 25 for a few reasons. So like that's the accuracy that was obtained over time, and it's probably saturated a bit. And the reason why it stopped is there was no check for contamination, and they, I mean, yeah, so the top solution, they could just consider the list of benchmarks they were kind of looking at and fine-tuning on the test set. And so they tried to fix it, but it was actually pretty hard, or like kind of impossible, because the line between fine-tuning on the test set actually can be tricky, and also it can be very hard to detect. So it was abandoned for this, and maybe, and it's interesting, I think, in this leaderboard, because it was widely successful, but then it was also widely criticized, because people were like, yeah, I mean, why do you do something with static benchmark where obviously you could fine tune on the test set, but I don't know, maybe it was, I mean, yeah, maybe it was obvious but it was still useful because, like, I don't know, I guess paper were doing it, and that was one way to do it automatically. But it's still like a massive, it's really a good thing for the community. So they sponsor a lot of compute through their platform, and all the data is publicly available. So it is used for research and so on. So now the chatbot arena leaderboard that was introduced in 2024. So I think it's the main platform to evaluate LLMs right now. And so it's highly dynamic by nature, because you go there and you ask whatever question. So the ratings that I showed, they're computed. It's not Elo rating, it's like another variant, but it's a similar model to compute the rating given a set of battles. And yeah, it mostly agrees with intuitive performance, so that's good. I don't know if you wonder how it works, but like, for instance, I asked a question and it picked this Quen3, I don't know, 200B, and what, I don't know, I don't remember what was the other one, maybe a Claude. But like, how do you sample the model is actually a question. I mean, actually, I'd be keen to ask, like, how would you sample the models if you were to build like chatbot arena? Mm-hmm. Okay, uniformly, I guess that would be the baseline. And do you think you could do better? Do you think you could do better? For instance, is it, well, I don't want to make it too easy. So, for instance, I mean, one model may be very weak, and then doesn't make sense to sample, like, battle with this weak model to a strong model as much, right? Whereas, like, if you have two very strong models, probably makes sense to sample kind of those pair more, because it's high. I mean, and I guess it's more uncertain, and that's, so it's really kind of, I guess, active sampling, like, important sampling. Yeah. Yes. Yes. What? Exactly, which is it's exactly the point I want to make. So, yeah. So that's count of okay. Okay, yeah, no, sorry. Yeah, left is the win rate of every model. So, for instance, GPT-4 has kind of a good win rate against a lot of models. So it's gets blue, and Llama 2 not that much, so it's less blue. And then you see on the right the number of battles that are sampled, and obviously, as you say, models that are better are sampled more because their ranking is more uncertain in sense. Okay, So which brings me like to this. So like the chatbot arena, it's they have, I think they say they have 3 million battles. They release, I think, 100,000. So that's 3% of the data. And it's a question, why do they not release the data set? So they, the claim is, I mean, basically the reason is like they say it avoids contamination. It avoids people just fine-tuning on the chatbot arena, because then maybe it will overfit to how much people like emojis and those sort of things. But the thing is, like private companies, they see a lot of data because of the previous plot I showed, and this important sampling rule, or active learning. And arguably, you would need a transparent leaderboard. Just on the previous one, so let me make that clear. So for instance, OpenAI, or actually it's this. Is it shown here? Yeah, I mean, I don't have the plot, but like for instance, OpenAI maybe has seen like 30% of the whole kind of set of battles, and like the like open source kind of developers of models, they've seen maybe 1% in addition to this 3% publicly released, and so that is really this big difference, and it's a bias that is enforcing the difference over time. In a sense, if you are interested in this topic, I highly recommend this paper, the leaderboard illusion, that discusses some issue that the chatbot arena has. I mean, and yeah, I mean the data access is one, but there are like a couple of others. Yes. Oh yeah, that's a great question. I also wanted to mention. So I was slightly annoyed because they changed all the interface, so it doesn't match my slide a week ago, and I also checked because I was highly suspecting they raised VC money, so they raised 100 million, I think, which also why, I mean, now they don't release the data, and I think it's the adage, like if you are not, I mean, you're not paying for to vote, so yeah, you are the product, so that's basically. But it's, I think I mean, it's okay, like everyone could do that, but the thing is, like, initially it started really as an open thing. They say they would release the data periodically, and it's slightly annoying. But so, yeah, there's a big need, I guess, for like a leaderboard that is maybe more transparent, shares the data, and so on, and so on. Yeah, and like, like some just a self-advertising detour. So maybe you, I mean, David, the other David, maybe mentioned that in his talk, but I want to point to this leaderboard for tabular data that we did. Yeah, I mean, here, like you see a bunch of methods, and yeah, I don't know, you can select, for instance, if you are only interested, let's say, in tree-based methods, and or if you want to see methods without, I mean, here we look at how well methods are improved with tuning and ensemble. And so I want to pitch it because, well, it's a leaderboard. I guess it fits in the leaderboard kind of subsection. Also, one reason I want to mention it is that it's actually very straightforward to do those leaderboards. So if you look at this gradual leaderboard, I mean, you can get a leaderboard in, I don't know, 30 minutes that is hosted, like the one I shared. And probably, I don't know, maybe there is a good leaderboard in your domain or whatever, and that's actually, it became much, much easier, I guess, thanks to Hugging Face in Gradio. So I highly recommend it. And of course, if you are interested in Tabular, I highly recommend to send something in this leaderboard. Okay, but back to LLM and wrapping up this part of the talk. So yeah, evaluating LLM is hard. There are many languages, many objectives. The cost can be high and can be highly ambiguous. So we have to do trade-off. For instance, trading off cost for accuracy. It is still early days. There are a lot of things that can be done. So for instance, achieving better trade-off, using multi-objective optimization, finding optimal sampling strategies. So when you have static benchmark with 100,000 examples. Which one do you pick? Which are the most informative? Those sort of things. And but I think overall, one of the key and maybe most important thing is to be able to evaluate low resource languages better, so that we also develop models that are kind of good for those lower resource languages. And I guess hopefully what I showed about the chatbot arena, it also shows that there is a big need for high quality leaderboards and that are transparent and so on. And so clearly for LLMs there is a space for one, but also in general it's good to have those. Okay, now I guess it will be the second part of the talk, which is slightly more focused toward AutoML. So I'll just mention at a very high level some application of AutoML and then dive deep into like a LLM as a judge and how to apply AutoML there. Okay, so clearly one AutoML thing is model selection. So like, for instance, just selecting the best model would be like an obvious AutoML task. So, among those models, okay, you can rank them, and so that maps their performance to like a number, but obviously they are not great or at the same thing. So some model may be very good at coding, but not so good to recommend trip to Hawaii. And how can you do this model selection given this? So I'm mentioning just this piece of work, which I think it's really like you could say I don't know AutoML paper, but it's really like this AutoML line of work where you have meta learning, some task features, and you use that to predict the best model. So what they do is they feed the prompt, for instance, recommend me a 2-day trip to Hawaii, to an LLM, and so this from this I think they sum up the kind of token embeddings, they get a vector, and they learn to project this vector to the ranking, and they learn from Chatbot Arena the weight of this classifier, and I think they call it prompt leaderboard, but mostly it's they learn a ranker that's kind of conditioned on the prompt, and then for every prompt they can, for instance, pick the top from the recommendation, or pick the top given a budget, and they show that they could get the best model, although it's from the author of Chatbot Arena, so they use all the data from Chatbot Arena. It's not available, so that's again, but it's still kind of interesting. And they claim that you could which makes sense, that you could get the top model in Chatbot Arena doing this routing. That sounds fair. There are like also startup and companies doing this. So for users also, like you may want to say, get an LLM for coding and not bother with this kind of routing and so on. And so there are companies that provide this service, so that either you can provide your benchmarks and they will learn the ranking given kind of stuff in your benchmarks, or like in general they can say, this model is, you're asking a coding question and then they route it to a model that is good at coding, those sort of things. And so there is space, I guess, for startup and also for research. That, there is still a lot of to do. For instance, you could do, in AutoML, there are very good techniques of transfer learning, meta learning, portfolio, which all could be used to improve this model selection. Okay, now I want to mention instruction tuning. I'm not sure how, I don't know how much familiar you are with instruction tuning, but if you remember the life cycle of an LLM, first it is pre-trained on a large corpus, and it just learns to predict the next token. But you can talk to it, so it's not useless. And then it goes a stage where it learns to talk to human. The way it works is like mainly 2 stages. The first is so-called SFT, like self-supervised training. Supervised fine-tuning, wrong wrong text here. And essentially, there are a lot of annotation generated initially by humans that, like, for instance, trip to Hawaii, like, okay, give me a 2-day trip to Hawaii, and a human write a 2-day trip to Hawaii, and you just learn to, I mean, you just fine-tune your model to this data set, so then it looks closer to something that can answer to instructions. And then there is an instruction tuning step. And then, like, for each instruction, you generate 2 completion, and you ask a human, say which one is better, and you optimize this. And you can optimize in different ways. So you can do online RL or offline RL. But, like, let's say for the AutoML perspective, it's just too, I don't know, just a Boolean. Do you use online? I mean, or it just, yeah, discrete choice. Right. And of course, there are, like, other approaches. Now, this instruction tuning pipeline is very important, but it has a lot of hyperparameters because you are undergoing several stages where you do fine tuning. You have to pick the base model to be used. You have to tune the optimizer, so you have to choose between Adam, SGD, or whatever. You have to pick the RLHF method. Maybe some LoRa hyperparameters. You have to pick the data set that you are using. So yeah, many choices that are super important. And so one thing is, like, arguably fine-tuning is becoming, or like post-training is becoming really the secret sauce. So, like, it's becoming clearer how to do pre-training for kind of everyone. It's just like not everyone is, like, another million of GPU hours at hand to do that. But maybe there's kind of slightly less secret, but the fine-tuning, I mean, there's a lot of kind of, well, secret things, secret data set or private data set. And so it would be good to be able to do that publicly so that the public models are good as well. To highlight this again, so if you pick at the time and look at, so it changes all the time, but it's always the same order of magnitude. So at the time I did those slides, the best open weight model was top 6, so that was DeepSeek. And the best open weight model with a code for post-training is 46, right? So there's a big gap. So you will, I mean, over time you will hope, if you get a very good instruction tuning, you should be able to get kind of top 6, because top 6 you have the pre-trained weights, and you have the fine-tuned thing. Just you don't know how to go from one to the other. Okay, and now I have a question for you. Yeah, why can't we just apply AutoML, like the best hyperparameter optimization that Chatbot Arena recommended us to this problem? And it will select the best, I don't know, RLHF hyperparameter dataset and so on. Mm-hmm. Okay, so we have, yeah, it's like kind of, you could think this is black box optimization, and the black box is the instruction tuning pipeline. So hyperparameters are like, yeah, kind of all optimization, hyperparameters, dataset, and so on. And you want to optimize this black box. So why can't you just do black box optimization?
We need to optimize for some metrics, and we do not really know which metric is actually right for that.
Exactly, yeah. That's the main issue. I mean, you could think there's a compute issue, so it's not cheap to try out 100 configuration, but the biggest issue is the evaluation. So I mean, that's in instruction tuning in general. There is also this difficulty that a lot of data sets are private, but now you have a lot that are public. So maybe you could still get good performance, but the evaluation, as you say, is the issue. So I mean, you could do black box optimization and use human annotation. That would be perfect, but every evaluation will cost about like a few $1,000s, and that will be the difficulty. Also, every time you need to wait a day to get human annotation. But so, for instance, if we take the best available open source pipeline, which is 46 in Chatbot Arena, so Tulu 3, what they did is, okay, so the data is not public, but they generated a lot of synthetic data. And for the evaluation, they use LLM as a judge. But they use a closed model, and now, I mean, and I don't remember the cost, but I think they spend a few tens of $1,000s on this LLM judge, because they call GPT-4 and it's kind of expensive. So I guess a question would be like, can we use AutoML to find kind of LLM judges that are kind of cheap, and ideally use open weights? Right. So I will talk about this now. So how can we apply AutoML to LLM judges? It applies multi-objective and multi-fidelity optimization. I don't know, who is familiar with multi-objective optimization? Like, it's just so that if I skip it or not. Okay, so maybe I don't skip it. I'll first start with a quick introduction on multi-objective and multi-fidelity optimization. Okay. So, yeah, optimization, black box optimization is often about optimizing a single objective. So what if we have many? And just as a motivating example, assume we were to pick a restaurant around here. The map is from last year, so it's Italian cities. So I did not update it with Tübingen, but you will get the idea. All right, so let's say we are here, and we look up at the restaurants. They have different rating, different distance. We don't want to walk far away, and we want to go to a nice place. So yeah, we want two things. And so how do we select which restaurant to go? So one way is that you could put every restaurant in a scatter plot. For instance, here we have these 4 choices, and now you want lower distance, higher ratings. And so clearly you don't have a single best solution. There is a restaurant that is very close, and there's a restaurant that has a very high rating, and in this case they are different. So there's just not a single best solution. And then there is a question, okay, but which configuration or which restaurant would you pick in this list? And so what you can notice, some choices are suboptimal. For instance, Le Marais is strictly worse because it is further than this restaurant, and it has lower rating. So rationally, you should just never go there. And in contrast, this restaurant, also this one and this one, it is optimal because there is no single restaurant that dominated for the 2 objectives. That is better at the 2 objectives at the same time. Okay, so that we say that if a configuration is worse for all metrics than another one, such as Le Marais, we'd say it is dominated. And so the set of non-dominated options, so it's called the Pareto front. It's put. Oh, sorry. It's put in red here. Okay. So Pareto front, we assume we have. Let's assume now that we want to minimize all the metrics. Formally, it's the set of configurations. We say that the formal definition of one configuration dominating the other is like it is better in all the metric and strictly better for one metric at least. And the Pareto front is the set of options that are not dominated by any other one. And so one question here is, think about in your head. Can you think about here, you want to minimize the 2 objectives, which configuration are on the Pareto front? And so here, like basically, that would be the configuration that are on the lower left, right? So like for those, you cannot find anything any configuration that dominates it. Whereas, like for instance, for this one, it is well, maybe that's harder to see, but like this one is dominated by this one because it's better in the two objectives. Okay, now I have a question that for you. So can you give me a procedure? So let's say I have this point cloud of objectives, and I want to find a procedure that will find deconfiguration that are in the Pareto front. So again, so I have endpoints that are d-dimensional. Can you find a procedure in linear time that will give like deconfiguration the Pareto front? So in this case, for instance, like you want a linear procedure that will find two configurations in dimension 2. Okay, I guess that's the hardest question from this talk. So you can pick the linear for every. Sorry, you can pick the configuration that minimize each objective, right? So for each I, you pick the configuration that minimize objective I, and this will be on the Pareto front. So for instance, in this case, if you pick the configuration that minimize Y1, that would be this one, and then Y2, it would be that one. They will always be in the Pareto front, and yeah, and you can do that in linear time. Okay. Okay, so that was multi-objective optimization. So we want to find the Pareto front. Those are the kind of best options that we can do. And they represent all the multi-objective trade-off. Now, multi-fidelity, so we are going to combine the two. Multi-fidelity is, it's about essentially using the fact that models are typically trained incrementally, so you don't train, let's say, neural network in one, just in one go. You train it epoch by epoch. At each epoch, you have a score. So can you, whether if there is a configuration that's very bad, rather than let it train for the whole thing, can you stop it earlier, right? So here in this case, we have 8 configurations. And so you could, after this budget, or like, I don't know, this number of epochs, so you clearly see that those one are worse. So, so you could just kill them. I mean, just stop running them. And you just let the top configuration running. And then you just continue over. So then the top configuration, after doing 25% of your budget, you let them run longer, and so on and so forth. So when a configuration is stopped, I mean, it depends on how you want to do it, but like for instance, maybe you don't want, if you have the machine with a fixed compute, you can just start something new and start with, the lowest budget and so on and so forth. And this is very, very efficient. It's a very efficient, I guess, hyperparameter optimization method. So here, I'm showing a lot of learning curves that if you were to run them all without early stopping to the left and with early stopping to the right, and you see that it will select much better configurations, like the bad configuration that are stopped early and they don't waste your budget. So it's an algorithm that works like really well. It can be parallelized, so it's very nice. But then one question like, okay, that's great, but how do we do that if we have multiple objectives? So here, obviously, I'm kind of sorting, and I'm with respect to one objective. But if I have 2 or 3, how do we do it? So yeah, so we need to adapt the sort procedure in a sense. Yeah, that's it. No. Yeah, it's a great point. I think most methods they will assume that cost is the same, but it's not. But like, of course, there are like some methods that extend that. But basic methods, they will assume the cost is the same. Yeah. Okay, so I mean, but basically, to apply multi-fidelity, we just need to be able to sort. So we just need to extend the sorting algorithm to handle multiple objectives. And actually, yeah. Like, do you have an idea on how you could extend the sorting to handle multiple objectives? So okay, so I have this point cloud. I mean, instead of having a vector, I have a matrix with the objectives. How can I sort it?
Prioritize the objectives.
Okay, yeah, that's I guess the lexicographic sort in a sense. So yeah, you could, yeah, that's one way. But yeah, but I guess most of the time you can't really kind of prioritize that. I mean, or lexicographic sort is really, I mean, also if it's continuous, it would not work that well because it would just end up sorting with one arbitrary objective, right? Mm-hmm. Okay, yeah. Yeah, it's good. That's pretty much like the one I have, which I think maybe kind of, I don't know, the best. So another abuse approach that you could think is like you could scalarize the objective. So you can back to the case one objective by just averaging up or doing a weighted average. But it has some issues because yeah, I mean, it can't handle every shape for the python. So for instance, it would fail if it's concave, but anyway, that's what you're suggesting is, I think, the best approach. So yeah, basically you could compute the python and then you say that that's the top ranks and you remove it, and then you compute the python again, that's the top rank amount what is left, and so on and so forth. So for instance, it looks like this. If you have this point cloud, you compute the python, those are top ranks, you remove it, then there's there are the orange left with, I guess, between 9 and 16 and so on and so forth. Where one thing is how do you break the ties, and there are like some heuristic to do that. So typically it's here, for instance, you see this, I mean, ideally you will want to find things that are how to say, points that are far from each other, because then they provide a good coverage given a low amount of sample. Yeah, but it's heuristic, and I don't know, there are like a few of them. Pick your preferred favorite, and that's it. So that's, but now we can sort, we can do multi-fidelity, so we can do multi-fidelity, multi-objective optimization. We just combine the two. And this has been proposed by several works. So here, it is a hypervolume, so distant Euclidean distance, kind of like the Pareto front that you were mentioning, and that's like the pink one is the one that has the lowest regret, and I don't know, that was also seen in a bunch of other works, so this works reasonably well. Okay, so we know how to do multi-fidelity, multi-objective optimization, so let's, good, and now let's look at tuning LLM judges. So again, an LLM as a judge is something that can, I don't know, score LLM outputs. And so you want the LLM judge to be cheap, and you want it to be accurate. You want it to be close to human annotation in a sense. So, and well, but the downside is like, yeah, okay, so the LLM as a judge, they can be biased, and they often rely on closed models. So, yeah, so what we want is we want to find kind of by tuning the LLM judge hyperparameter, we want to find judges that are highly accurate and ideally that have a low cost. And of course use open models, because then we are clearly better, because we can't have something where a GPT-4 favors itself, and also we just have a easier artifact to analyze. Okay, so tuning LLM judges. So like, what can we configure? What is the search space? So the biggest part is, the most important part is probably the prompt. So how do you ask your LLM judge to pick between output 1 and output 2? And to the right, I gave one example. And this you can parameterize in some way. So you can say, I don't know, I have a Boolean flag, whether or not I would ask the LLM judge to provide its answer, because maybe providing its answer makes things better, to provide an explanation, because maybe if it provides an explanation first, it will make a better decision. How the score, I mean, how the LLM judge output is score, because this is also quite, I mean, there's also a lot of degree of freedom, and we don't really know which one is the best. Yeah, so we can parameterize all of this. And so basically, in this case, like 80 prompts that you can generate on the fly, given kind of some Booleans. In addition, obviously, we want to find a good base model for the judge, right? So we could pick, for instance, Llama 3 or Qwen 2. And so we add in the search space 7 open weight options for temperature, because, for LM inference, the temperature is quite important. And yeah, and finally, we also have a Boolean whether or not we generate a prediction with output 1 and output 2, and then again by swapping the answer and taking the average. Okay, so in total, this gives about 4,500 possible judges. And so if we will brute force this, so like evaluating the way it was evaluated before, that would cost $2 million. So like we want to reduce this cost. Okay, and to reduce it, we are going to do two things. So one is that we're going to do multi-objective, because we have accuracy and cost that we want to optimize. And yeah, we're going to do multi-fidelity as well. Before, I guess this work, I think LLMs, judges were mostly manually selected and also evaluated. And as I said, there was like issue with cross validation. So they were used in the same, they didn't have validation set. So a bit annoying. But and there you see, for instance, like some configuration that were evaluated from Alpaca eval, and so every time they will evaluate a judge, and for instance here try a chain of thought or something, try a different reference model, and yeah, and so that something that you want to tune. So now one problem with, I guess, this is not really, how to say, it was not really a paper about how you can do hyperparameter optimization, just the way people were doing it. So they were evaluating a few configuration. To evaluate a configuration, it is very expensive, because they need to, for this LLM judge configuration, they need to annotate the output of many models on many prompts, so on a grid of models and prompts, because they are kind of comparing the ranking. So it means that it makes things kind of very expensive. And so what we did is, instead we first identify a metric that's cheaper than doing this dense grid and then experiment correlation to compare the ranking. And we use multi-fidelity, multi-objective optimization then to tune the configuration. Okay, for the metrics of the judge, we have, basically two basic choices. One is kind of Spearman correlation, what was done before. So you evaluate a list of LLMs on a list of prompts, or a grid of models on a grid of a grid of models on a list of prompts. And then you call your LLM judge configuration on each of them. And you compute a win rate, and you compare this win rate with Chatbot Arena ranking. And this gives you a score between 0 and 1. Yeah. The second option is, well, you can take a list of annotated preferences by human, and you just compare on average how often your LLM judge has the same kind of prediction. And yeah, and this is just a stupid question, but like, which one is better? And from those two metrics. And so one way to look at it is like which one has a better signal to noise ratio. And so what we did is that we look for not scaling laws, but like we looked like for the first case, for instance, if we increase the number of instructions, what happens for the ranking of where we just change a base model number of parameters of the judge, right? So here this is a judge with like 500 million parameters, then it's a judge with 1 billion parameter, and so on and so forth. There are also different data set of instructions, so we look at all of them, and the thing is like even using a combination of instructions, and you can't really distinguish like a judge that has 32 billion parameters from a judge that has 72 billion parameters with this metric, so you will need more instructions. So it's not a good sign. On contrast, this second option, so this human agreement, so we can also increase the number of instructions, and we see the scores that we have. As it's much more stationary, and we can see, I mean, we will need to zoom, but the confidence interval for the 32B and 72B billion parameters judge, they don't overlap. And you can also look at the signal to noise ratio, so you take the mean divided by, the standard deviation divided by the mean, and you see that it's basically with the same number of instructions. The second metric is 1% variation. In a sense, it's an 8% variation with our metric. So yeah, so it's clearly much better to do the second metric. So that's a metric that we optimize. Okay, and then we do multi-fidelity, multi-objective optimization finally. So we have 4,480 configuration. We evaluate them on a small set of instructions. Then we pick the top, and we evaluate them on a larger set of instructions. Then we pick the top, and we evaluate on all the validation set instructions. And yeah, we need to sort, but now you know that you can do non-dominated sort. So this thing that we saw earlier, and here in particular, this is all the judge configuration. We can sort the top configuration, and those we evaluate them longer, and yeah, and ultimately we end up with just a few number of selected configurations. So just quickly some empirical results. So we get a continuous set of judges. I think we have 400 divided by 3. I actually don't remember how many we selected at the end, but that gives a continuous set of trade-off. From this, we just select 3, small, medium, large, because people like to have, like, 3 different sizes, because they have different GPUs, so that's why we don't, report the whole part to front. We report on 3 data sets. One is a LM6 test set, so that's battles from Chatbot Arena, but on test instructions, so like instructions that were not seen, and there, I guess the human agreements is what we are optimizing for the validation, for validation score, and we report what we have, and so we basically match the performance of like judges with GPT-4 So that Arena Hard used GPT-4o, so it's a much more expensive model, but at a cost that is kind of half. So we do decrease the cost by a lot. And then we look at other, because there are a lot of LLM judge, I guess, benchmarks. So we look at this one where we compare with previous work that have an approach that fine-tune the LLM judge to predict the label, or output 1 and output 2. So we compare something that is fine-tuned to a data set, whereas we don't fine-tune, it's just like purely zero shot with a configuration. We selected something completely different. And I don't know, like the human agreement is much, much higher. Like, I don't know, we have, I mean, all the judges have like a human agreements larger than 67, whereas like the fine-tune approaches, yeah, which just 67. And the last one, we compare on the Arena Hard with Spearman correlation, which again is not the metric that we optimize, but we can still match the performance of like close kind of LLM judges while decreasing the cost in this case, I think by 100. I think I was, okay, maybe I'll just do this one quick and then skip the rest of this part. Yeah, we also analyzed, okay, which, how to say, which hyperparameter is important for LLM judge, so like to help people to design better judge in the future. Okay, maybe I skip for the sake of time. Right. So to conclude this part, LLM judges, they can be tuned at a reasonable cost with AutoML. Applying AutoML, it allows to match or outperform kind of previous approaches while diminishing the cost significantly and using only open weight models. Next step and future work. So we want to use those open weights models. So for us, it's quite important. They're quite important in the model development, but now we can rely on models that are at least a bit more open. Then I think so. This also opens the door to do this automatic instruction tuning that we were mentioning, because now you could optimize this evaluation metric that becomes much cheaper. And generally, I think there's still, of course, a lot of room for improvement on applying AutoML for judges. The multi-fidelity, multi-objective approach that I shown, for instance, just use random search or brute force search or grid search on the initial candidates. But of course, you could do something model-based and do much better, do ensemble portfolio. Just in case you're interested, that all the data is available. So a lot of things you can just simulate by doing table lookups from this. Okay, now the last part of my talk, which is not completely related to LLM evaluation, but related to LLM. It's discussion about, I guess, openness. So just I was looking for the most expensive project built by humanity, and I found LHT, and I guess this, which cost 5 billion and involved 23 countries. This one was actually, I don't know what would be the cost and if it will be made, but there's like Hubble that costs like 16 billion and involved 11 countries. ITER, which is experimental fusion reactor, it costs 45 billion and involved 33 countries. And this one, Zoom, is hiding, but it's an international space station. And and costs 100 billion and 16 countries. There is an example like where it didn't involve like that much cooperation, and it's a Manhattan project. It still involved like 3 countries, but I think, yeah, you you see what I mean. And for LLMs, the current situation is really a harm race. So like we've got big tech companies competing, and you have a world where you have n actors developing n models completely independently, not sharing anything. So that's a ranking on Chatbot Arena over time, and yeah, they are dominated by Google, OpenAI, and those kind of companies. It could be fine if this would have no incidence on the world, but it does have I guess right now it's still okay, but it's going to go. The consequence is going to be larger and larger because one way to make those models better is to scale up the compute. This is one of the most efficient things that we know to improve their performance, and here you see the dollar cost associated with LLM training, and it doesn't reach this $1 billion that I was showing before, like for Hubble of the International Space Station, but it's still a few hundred millions, and clearly we will likely have one cost model that costs like $1 billion to be trained in the near future. And okay, so there are like some things that are helping. So like some things that like algorithmic progress. So the same model, like if you want to reach the same perplexity, the same quality, the cost is decreasing very fast because the GPU are improving, but also just like the algorithm are improving. So we have better, optimizer, better everything. And this progress is estimated to be like 4x per year. So every time like the cost to train the same quality decreased by 4 just because of algorithm and coding. But the thing is like this cost is immediately reinvested because like then you get better models. So that's annoying thing. And there is an alternate model, obviously, where companies, universities share open weight model, sometimes fully open models and code. And so, for instance, Meta, Google, Mistral shared a lot, and they're like fully open models also that has been shared by university, but also like, for instance, Apple. So companies also sometimes do it. So maybe you're like, yeah, but it's nice, but you can't collaborate for profit. As two, I don't know, things you cannot reconciliate. Just want to highlight that, okay, so AI right now rely on GPUs, obviously. And this is based on one of the biggest industrial collaboration in history. So do you know what is a critical technology that kind of powers GPU? That I guess rely on this collaboration, but exactly. And what?
And size that produces the mirrors.
Yeah. So it's actually you're pointing out at this collaboration. So the ASML, like the company that assembled this machine, is based in Netherlands. They're using mirrors, kind of in Germany, and that's like I'm not sure they're like another company on Earth that can do mirror that good and so on. And it rely on a lot of other pieces, and it's really the core technology that's powering AI. So that's one of these extreme ultraviolet machine. It costs like 400 million to buy one. In case you are interested, they are all sold out. It prints really kind of chips, silicons at a precision that is order of magnitudes better than standard machines, and in this case, the cost of EUV costed like between 14 and 21 billion, but it involved like many countries over decades of kind of research, and it's really the result of a large-scale kind of collaboration. It's built by ASML, which is like EU company, so that's also a great presence for EU in the kind of the tech scene. Yeah, and it's a very important company, like in the strategy of like how AI is diffused and so on. If you're interested, I recommend reading those. And just before concluding, I think, okay, I made a case for openness. Kata mentioned that I am working with Aaron in the room also in OpenULLM. So it is a very large effort by EU to build model multilingual LLMs completely from scratch, completely open, weight, code, and data. It has a very large funding, so that it has like 40 million euros funding for to hire very smart people. It has also many million of GPU hours allocated in European clusters. So It started just in February, so we don't have a 7TB model that is state of the art yet, obviously. We are going to release models soon at like a small scale. I mean, we obviously are starting small. So here those are the models that we are going to release. The x-axis is the training flop that is being spent, and the y-axis is the performance. And so we are trying to establish kind of scaling laws in a sense. And in this case, we really wanted to see, okay, how good can we get with by doing our best into the whole kind of code base and using public data sets. We're currently hiring, so if you are interested in those sort of projects, please ping me or Aaron. And so, yeah, the next thing that we're going to do is like, go to larger compute and hopefully beat those models. And obviously, there are a lot of areas to apply AutoML, not just, but yeah, I mean, for pre-training, post-training evaluation, and so on. Yeah, I hope you have maybe a slightly clearer picture about the LLM evaluation landscape, that you understand why it can be difficult to evaluate a model that produce just arbitrary text, and given this all these many dimensions, like kind of languages, different objectives, the high cost associated to it. I also hope I show you that AutoML has a lot to say to make those processes more efficient, like many objectives. Like, of course, when we see that, we think about multi-objective optimization. Also, we have a lot to say to make those kind of cheaper, which is, the cost is really a big issue right now. And yeah, thanks a lot for your time.